Welcome back. In our last video, we mastered logistic regression. We learned it's a fantastic model that finds the best straight line, or linear boundary, to separate our data. But this leads to a critical question. What happens when our data isn't linear? Look at this. Here we have class A inside class B. How can a straight line ever separate these? It's impossible. Logistic regression will fail completely on this problem. We need a new kind of model, one that doesn't think in straight lines.
For this, we turn to one of the most intuitive models in all of machine learning, the decision tree. A decision tree works exactly how it sounds, like a flowchart. It's a series of if-then questions that chop up the data until it can make a decision. This is what we call a white box model. We can look inside and understand exactly why it made the prediction it did. It's like a game of 20 questions. The model learns the best questions to ask to isolate the classes. Let's learn the lingo. It's simple. The node at the very top, where it all begins, is called the root node. This is the first question the model asks. Any node that splits is called an internal node, and the split itself is a branch. And most importantly, the nodes at the very end, the ones that don't split and just give you the final answer, are called leaf nodes. So data flows from the root, down the branches, to a leaf. Here's a classic simple example. Let's try to predict if a passenger on the Titanic survived. The root node might ask, is the passenger male? If yes, we go down one branch and ask a new question. Was their age over 10? If yes again, the leaf node predicts, did not survive. If we go back, and the answer to male was no, so female, we go down a different branch. Was their ticket third class? If yes, predict did not survive. If no, predict survived. You see? It's just a set of rules. So how does this relate to our nonlinear data? Here's the key. Each question a tree asks is a split in the data, and these splits are always axis aligned. They're just simple vertical or horizontal lines. The model doesn't find a fancy diagonal line. It just asks, is x less than 5? And bam, a vertical split. Then it asks, is y greater than 3? B-A-M, a horizontal split. It just keeps carving up the space. Let's watch it solve our donut problem. The root node might ask, is x less than 7? And it draws this line. That's split 1. Now it looks at the left and right sides independently. On the left side, it asks, is y greater than 5? Split 2. On the right side, it might ask, is y greater than 3? Split 3. And it keeps going, adding more lines inside these new boxes until, voila! The data is perfectly separated into rectangular regions. Each one of these final boxes is a leaf node. This is how it handles nonlinear data. Making a prediction is now incredibly easy. Let's say we get a new data point. We just drop it into our flowchart. Is its x value less than 7? Yes. We follow that branch. Is its y value greater than 5? Yes. We follow that branch. We've hit a leaf node, and this leaf node's rule is predict class A. That's our answer. It's just a simple, fast lookup. This all looks great, but it leads to the $1 million question. How did the tree know what question to ask first? Why did it pick, is x less than 7? And not, is y greater than 3? It could have made thousands of different splits. How does it find the best one? The answer is that it searches for the split that makes the new nodes as pure as possible. What is purity? It's simple. A node is perfectly pure if all the data inside it belongs to a single class. Imagine a box with 50 Class A points and 0 Class B points. It's 100% pure. We can stop. That's a leaf node. Now, imagine a node that's perfectly impure. This would be a 50-50 split, 25 Class A and 25 Class B. This node is useless. It's a coin flip. The entire goal of the algorithm is to find splits that take impure nodes and turn them into purer child nodes. We need a way to score this impurity. The most common metric is the Gini Impurity score. All you need to know is that it's a score between 0.0 and 0.5. A Gini score of 0.0 is perfect purity, all one class. A Gini score of 0.5 is perfect impurity, a 50-50 split. The model's goal is to make splits that drive the Gini score down towards 0. So how is it calculated? The Gini score answers this one question. If I randomly grab an item from this node and then randomly guess its class, what's the probability I'm wrong? Think about it. In a 50-50 node, my chances of being wrong are 50%. The Gini score is 0.5. In a 100% pure node, if I always guess that one class, my chance of being wrong is 0%. The Gini score is 0.0. A node that's 90% class A and 10% class B, my chance of being wrong is low, but not 0. The Gini score is 0.18. That's all it is, a measure of how likely you are to be wrong. Now we can put it all together. The algorithm finds the best split using a process called information gain. It's simple. First, it calculates the Gini score of the current parent node. Let's say it's 0.45. Then, it tries a potential split, like is X dollars less than 5? And calculates the new Gini scores for the two child nodes it creates. Maybe the new scores are 0.1 and 0.3. The information gain is just the reduction in Gini. We started at 0.45 and ended at an average of 0.2. The gain is 0.25. The tree does this for thousands of possible splits and picks the one split that gives the highest possible information gain. Let's look at a concrete example. Our parent node is perfectly impure, 100 class A, 100 class B, Gini equals 0.5. The tree tests, split A is X dollars less than 5. This gives us two new nodes, but they're still pretty mixed. Their Gini scores are 0.3 and 0.35. That's some information gain, but not great. Then it tests split B. Is Y greater than 3? This split perfectly separates the data, creating two very pure nodes with Gini scores of 0.1 and 0.15. The winner is clear. Split B has the highest information gain, so the tree chooses this as its split. And this is how the tree grows itself. It's a recursive process. It starts at the root node and finds the single best split, BAM. Now it has two new child nodes. It then treats each of those child nodes as a brand new, smaller problem. It looks at the left node and asks, what's the best possible split for this data? BAM. It splits. Then it moves to the right node. What's the best split here? BAM. It just repeats this process over and over until the nodes are 100% pure or it hits a limit we set. Now we come to the single biggest weakness of decision trees, overfitting. If we let the tree keep splitting until every single leaf is 100% pure, it will essentially memorize our training data. It will learn every single quirk, every piece of noise, and every outlier. Look at this. To get 100% purity, the tree had to make a tiny, ridiculous little box just to catch that one red dot that was in the blue zone. This model is perfect on the data it trained on. But what happens when we give it new data? It will be terrible because it's learned the noise, not the pattern. This is what that overfitting looks like. On the left, we have a simple tree. It only made 2 or 3 splits. The boundary is clean and it captures the general trend of the data. It might get 1 or 2 points wrong, but that's okay. On the right, we have a deeply overfit tree. It has a crazy, jagged, complex boundary that makes no sense. It's perfect on this data, but it's a useless model in the real world. It has no idea what the actual pattern is. So, how do we fix this? We prune the tree. The easiest way to do this is to simply stop it from growing in the first place. When we create our model, we give it a hyperparameter called max depth. We might say max depth equals 5. This is a rule for the model. It's not allowed to grow more than 5 levels deep. This forces the tree to only find the most important, highest information gain splits. and it's not allowed to waste time creating tiny boxes for outliers. It's the #1 way to prevent overfitting. Besides max depth, we have other tools. We can set mine samples Chassagne split. This tells the tree, don't even bother splitting a node unless it has at least 20 samples in it. This stops it from splitting on a tiny group of 3. We can also set mine samples leaf. This says your final leaf nodes must have at least 10 samples in them. All these rules work together to stop the tree from memorizing and force it to find general patterns. So, let's summarize. The pros of decision trees are huge. They are super easy to interpret. You can literally print out the flowchart and show it to your boss. They naturally handle nonlinear data, which models like logistic regression can't. And they don't even need their data to be scaled. But the cons are also serious. They are extremely prone to overfitting if you don't control them. And they can be unstable. A tiny change in your data can sometimes cause the entire tree structure to change. So, to recap. Decision trees are flowcharts that carve data into boxes. They learn by finding splits that reduce impurity, measured by the Gini score. The process of finding the best split is called maximizing information gain. Their $1 weakness is overfitting, which we solve with pruning, like setting a max depth. This leads us to a fascinating idea. We know one tree is unstable and prone to overfitting. So what if, instead of one perfect tree, we built hundreds of small simple trees and let them vote on the final answer? That, my friends, is called a random forest, and it's the topic of our next video. Subscribe, and I'll see you there.